Hello friends, and welcome to yet another video where we discuss about questions which are relevant for NEET and JEE question papers. Today I have come with a very new method which will in turn help you revise the chapter called Electrostatics very faster. If you are new to my videos, please consider subscribing it and hit that bell icon so that you get all my notifications whenever I upload a new video for you. So my name is Naveen Kumar and you're watching my YouTube channel. So we start with the first question. Two metallic spheres of radius 1 centimeter and 3 centimeters are given charges minus 1 into 10 power minus 2 coulomb and 5 into 10 power minus 2 coulomb respectively. These are connected by a conducting wire. The final charge on the bigger sphere is. So here we are given with two radii. Let's draw that two spheres. Let's draw this two spheres. This is a smaller sphere and we have a comparatively bigger sphere over there with radii. Let's call this a radii as r1 and this as r2. So here one is r1 is given as 1 centimeter and r2 is given as 3 centimeters. So these charges are connected by a thin conducting wire. So one of this particular this sphere that is carrying a charge of minus 1 into 10 power minus 2 coulomb, and here this carries a charge of 5 into 10 power minus 2 coulomb, is joined together by a conducting wire. So what actually happens when these two are joined together? You know that the charge starts to move together. One is a negative charge, the other is a positive charge. It starts to move together, making sure that the charge stops its motion when the potential on the first sphere and the potential on the other sphere becomes equal. So you get it. When the potential becomes same, no more charges tends to move. So let's calculate and write down. We'll put the charge, the first charge Q1 here as minus 1 into 10 power minus 2 coulomb and Q2 here as 5 into 10 power minus 2 coulomb. So when you add these two together, you will get the total charge is equal to Q1 plus Q2, which is the sum of minus 1 into 10 power minus 2 coulomb and 5 into 10 to the power minus 2 coulomb, 10 to the power minus 2 coulomb. So this is the total charge which is supposed to be there between the two charges. So now what are the specifications which are shown over here? First sphere is having a charge minus 1 into 10 power minus 2 coulomb and the second sphere having a charge of 5 into 10 power minus 2 coulomb will stop its motion when the potential becomes same. So the potential on the first sphere becomes equal to the potential on the second sphere. So what's the equation for potentials? You already know this equation. 1 by 4 pi epsilon naught. The charge over it, let's call it now the remaining charges Q1. So divided by the radius R1 becomes equal to 1 by 4 pi epsilon naught the second charge Q2 divided by R2. Don't get confused. Here R1 and Q1 and Q2, which we have said as minus 1 to 10 power minus 2 coulomb and 5 into 10 power minus 2 coulomb no more exist. It doesn't exist anymore. Now this new Q1 and Q2 which are defined in the potentials and new charges which are remaining on the first sphere and the second sphere. Don't get it mixed. Now our main question was to find out what is the total final charge on the bigger sphere. Final charge on the bigger sphere as Q2. We have to find out Q2. So with this, Q1 divided by R1 becomes equal to Q2 divided by R2. We are given with R1 and R2. So if you take the ratio of R1 by R2, R1 divided by R2 is equal to 1 is to 3. So what you are going to get with the next value also, you can also get it as Q1 plus Q2 is equal to 4 into 10 power minus 2 coulomb, and Q1 divided by Q2 is also 1 by 3. So R1 divided by R2 is equal to 1 by 3. So what you can do from here, you can find out as Q1 divided by Q2 will be equal to R1 divided by R2. So if 1 by R1 by R2, you already know it, R1 by R2 is 1 by 3. So if I substitute this, you will get it as Q1 divided by Q2 is equal to 1 by 3. From here, you could even say that 1 is equal to, from here, Q1 is equal to Q2 divided by 3. Why we have to find out like this is, we have to find out the final charge on the bigger sphere, that is Q2. That means the final answer should have only Q2 in this equation. So let's call this as with a beautiful number, let's call this as equation number 2. Probably where is the equation number 1? Definitely this is equation number 1. Using this equation 1 and 2's, equation 1 and 2, we could substitute for Q1 in this substitution for Q1 in this particular equation, you will get it as Q2 divided by 3 plus Q2 you will get is equal to 4 into 10 power minus 2 coulomb. So the remaining part of the derivation is definitely you have to take the LCM, and you will definitely find out Q2, that's the charge on the bigger sphere, you will get is equal to 3 into 10 to the power minus 2 coulomb if you take the LCM. So if you look at the options, you will get it as 3 into 10 to the power minus 2 coulomb, which is the right answer. So let's look at this particular question. The electric field at a distance 3r by 2 from the center of a charged conducting spherical shell of radius capital R is E. So what is given? At a distance of 3r by 2 from the center of the conducting spherical shell, it's having radius, obviously the radius of the sphere is capital R, the electric field is given as E. The electric field at a distance r by 2 from the center of the sphere is. So let's draw this figure and find out if what they are saying is can we replicate that in a figure. Okay, now let's draw a sphere here. Now this is a sphere, right? Okay, it has a radius, you already know it, it has a radius, let's call this radius as capital R. Okay, now the electric field at a distance 3r by 2, that means definitely if 3r by 2 is a point outside the sphere, that means it is definitely bigger than r. So that means the point will be definitely outside the sphere. Okay, let's draw this outside the sphere. Let's take this as that point. So this r is, this particular distance is 3r by 2, where you have the electric field is given as E. Okay, now the charge is definitely the sphere is charged. So what will happen if you supply some positive charge on the sphere, conducting sphere? What will happen? The basic idea behind it is, due to electrostatic repulsion, all the charges tends to move to the maximum possible distance which is onto the surface. Okay, why? Because it's a conducting sphere, it can, the charges can move. So all the charges will start accumulating, all these charges will start accumulating on the surface, which I have roughly shown it with the positive charges which are distributed like this. So what actually happens is, there is no more charge actually inside the sphere. Since there is no electric field or charge inside the sphere, definitely the electric field is a 0 inside the sphere. So according to the question, outside, which is 3r by 2, the electric field is E, which is already there. The electric field at a distance r by 2, definitely r by 2 is a point which is definitely right inside the sphere. At a distance r by 2, since you don't have any charges inside the sphere, the electric field will be definitely equal to 0. So this is a concept which is connected to electric field And what actually happens if you supply some charge on a conducting sphere? The point highlight here is all the charge will start accumulating on the surface only, making sure that there is no charge inside the sphere. So the case is the potential which is right at the center of the sphere and the potential on the surface will be seen, so that there is no potential difference between the center and the surface. If there is no potential difference, the electric field, obviously you know it, equal to 0. So the electric field here inside is 0, which is this location. So the answer is 0. Let's look at the next question. Three capacitors, each of charge C and of breakdown voltage, that means the applied potential is V, are joined in series. The capacitance and breakdown voltage of the combination is. The combination is definitely we are combining that in series. So let's draw this figure and see how it all works out. So this is your first capacitor. It's connected to the next capacitor and it's definitely connected to the next capacitor. All are having a breakdown voltage. What they have said is the voltage applied is V, the next voltage applied is V, and the next is obviously V. Okay. Now, if these are connected in series, the capacitances are C, C, and C. So when you are connecting this in series, the effective potential, the total potential will be definitely the sum of V plus V plus V. Since they are connected in series, the potential will be equal to 3V. So obviously 3V is the total potential. Now since they are connected in series, the capacitance will be 1 by C equivalent capacitance equal to 1 by C1 plus 1 by C2. I should not write it. Why? Basically all the capacitances are same. So to formulate the equation, we'll write it as 1 by C1 plus 1 by C2 plus 1 by C3. So after the substitution gets you 1 by C plus 1 by C plus 1 by C. So 1 by C equivalent, you could see that the denominators are same, so that the numerators gets added together, that you will get it as 3 divided by C. 1 by C equivalent is that. So what will be C equivalent then? The C equivalent will be equal to C divided by 3. So you obviously got the answers. The potential will be 3V and the capacitance will be C by 3. The potential is 3V and the capacitance is C by 3. So the right answer is the fourth option. Let's look at this question. A series combination of N1 capacitors, that means there are N1 number of capacitors, each of value C1, that means all the capacitors do have the same capacitance as C1, is charged by a source of potential difference 4V. That means the total potential applied is 4V. When another parallel combination of N2 capacitors, now this is not series, this is parallel. When combination of N2 capacitors connected in parallel, each of value C2, all those are having the same C2 capacitances, is charged by a source of potential difference V. It has the same total energy stored in it as the first combination. So what is given here as a hint? In both the cases, the energies are same. So obviously our idea is find out the energy, total energy for the series combination, find out the energy for the parallel combination, equate it. Then what you have to do, ask the combination, the value of C2 in terms of C1. So when you equate this two, you probably get the combination of, so the value of C2 in terms of C1. So let's start doing it. Let's start with a series combination. That's the first part of the question. Series combination. So in the series combination, we'll find that the series combination do have an equation. 1 by Cs, we'll write it, is equal to 1 by C1, first capacitance, plus 1 by, obviously it should be C2, but the capacitances are the same. So we'll write the C1 plus 1 by C1 plus 1 by C1 and so on. How many are there? N numbers are there, so you add as the last number is The last one will be n times C1. The last one will be 1. So when you, what you do is, when you find out the total capacitance, what you do is Cs is equal to 1 plus 1 plus, how many are there? N1 number of capacitance, you will write as N1 divided by C1, or Cs will be equal to C1 divided by N1. So this is the series combination of capacitors which are joining over there. So what happens now when you start with calculating energy in series combination, energy in series combination, what is the equation? The equation will be obviously half CV square, CV, capacitance in series combination, V square, V in series combination square. But in series combination, we have already said that in our question itself, it is specified that the total potential is 4V. That means Vs will be substituted as 4V, the potential in series combination. So what will be the answer? Which is equal to half of Cs, which is given as C1 divided by N1 multiplied by 4V the whole square. 8 C1 V square, if you substitute it, you will get divided by N1. Okay, now let's do it for parallel combination. Parallel combination, we have said that in the question it is said that potential applied is V according to that question. That means the potential difference applied is V. It has, okay, and the capacitance is a C2. So in parallel combination, let's write it for parallel combination. For parallel combination, yes, for parallel combination, so we have an equation Cp, you'll write as parallel combination do have a resultant capacitance equal to C1 plus C2 plus C3 plus so on. So here it is given as C2, 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 C2. So how many will be there? N2 numbers are given there according to the question. N2 capacitors are there. So the total capacitance is equal to N2 times a C2. You obviously will be able to understand that, right? C2 plus C2 plus C2 plus C2. How many are there? N2. So when you add it together, it gets N2 times a C2. Okay, now the potential applied is V. Okay, now the capacitance, so the energy stored will be equal to energy stored in the parallel combination. Energy stored in the parallel combination is half CV. That means CV square. CV square. Capacitance multiplied by potential square. What is the capacitance? A Cp is the capacitance potential in the parallel combination square. Let's put it in substitution. The next sentence, half of Cp is N2 times a C2 multiplied by Vp is, as you already know, the potential is same for all the capacitance in parallel combination, which is already given as V. So as you scroll down, you will obviously come understanding that it is equal to N2 C2 V square divided by 2. So in our question it is already specified by the energies as same. How will you substitute the energy in the series combination is equal to the energy in the parallel combination. So energy in the series combination, if you go back, you will understand that energy in the series combination was this. So if I substitute that here, you will get it as 8 C1 V square divided by N1 becomes equal to N2 C2 V square divided by 2. So when you substitute that, you will get C2 equal to 16 times C1 divided by N1 N2. Yeah, 16 times C1 divided by N1 N2, which is the right answer, which is the fourth option is the right answer. So let's look at this particular question. 4 equal charges plus Q, minus Q and minus Q are placed at the corners of a square of side length 2L as shown in the figure. Yes, side length 2L. So we can actually draw it and show you. This side length will be 2L for probably since it's a square, all the sides will have 2L 2L length specifications. So the electric potential at a point A midway between the two charges, which is plus Q and plus Q, is, you have to find out the potential here. So which is the midway between them. So for simplicity, what you do here is we just join this to this particular point as well, so to make our figure more clear, the figure more clear. So obviously what will be this distance? Obviously this distance is L, this distance is L. So we have to find out the total potential at this location. For that, I'll just name this points. Here I've already taken it as A, so I'll put this particular point as B, this let it be C, this is D, and this is E. Okay, so before we actually proceed to finding the total potential at the point A, let's calculate the distance AC and AD. You obviously, from the figure, you will be able to understand that both are same. What are the things which are same here? AD becomes equal to AC. How will I calculate that? Apply Pythagoras theorem for that. Square root of, yes, this side square plus this side square. This side is 2L, you already know that. You can write it actually as AB square plus BC square. BC square. So what you will get? You will get an answer, square root of AB square. What is AB? AB is L square plus BC is, BC as you already know it is equal to 2L. So you will substitute it as 2L the whole square, and you can look at the options. These are the four options which are given over there. Any of the one will be the right answer. So that is what we have to actually find out. When you substitute this, you will get it is equal to root 5 times L, okay, which is both the values for AD and AC. So in our derivation, we'll be able to use both. Okay, we have to find out the total potential at the point A. So what is the total potential at the point A? The total potential at the point A is the contribution of the charges which are kept at the point B, plus we are applying superposition principle for this, potential which is kept at the point C, plus the potential which is kept at the point D, and obviously the last one, potential kept at the point E. We just have to add all these things together. Starting to substitute it, we have the potential at the point B as plus Q. So we have the equation 1 by 4 pi epsilon naught plus Q divided by the distance. What is the distance from till at the point A because of the charge kept at the point B? What is the charge? It's a positive charge. So what is that distance? The distance is L. So that is it. Plus similarly the potential at the point C will be this. So the distance is AC. So what you have to do, 1 by 4 pi epsilon naught. What kind of charge it is? It's a minus charge. Similarly minus Q divided by the distances. This distance, as you already know it as AC distance, we have already calculated that it's equal to root 5 times L plus remaining. Potential at the point D will be potential at the point A because of the charge at the point charge minus Q. So you get it as 1 by 4 pi epsilon naught, yeah, minus Q divided by the distance. What is the distance? AD. What is AD? Root 5 times L plus the last one, potential at the point A because of the charge kept at plus E at the point E. So you get it as 1 by 4 pi epsilon naught into plus Q divided by the distance, which is L. So you are using basic equation. What is that? The equation for potential at the point is equal to 1 by 4 pi epsilon naught, the charge divided by the distance from the point of the charge to where you are finding out the potential, the distance. So if you are substituting all this together, you will probably end up taking common values, and you will probably end up substituting 2Q divided by 4 pi epsilon naught times L in the denominator. You can take common, remaining you will get it as 1 minus 1 by root over 5. So this is your right answer, which will probably fetch you which answer is the right answer. Definitely the fourth option is the right answer. So let's look at this particular question. Two pitch balls, that means you can take it as a charged balls, carrying equal charges are suspended. They're both carrying equal charges. Means here one charge is here, there's another charge over there. Suspended from a common point by a string of equal length. That means the length of the strings are equal. The left figure, I'm talking about the left figure, and they are separated by a distance which we call it equilibrium separation. The distance is r. Now the strings are rigidly clamped at half the height. That means you are making that point to be joined at that particular center half distance, so that clamped at half the height, the equilibrium separation between the ball now becomes, now that distance become r dash. The distance is going to change. The distance between the two charges definitely going to change. The distance definitely going to change. What is that relation connecting r dash and r? So that is our question. So let's start with our basic ideas. Now this, what is this? These are the answers for r dash is equal to, r dash means this distance is equal to what in terms of small r. Okay, these are the four options which are given to you. So if you look at this, let's start by analyzing this figure. Let's look at this particular figure. Y is the displacement which is measured from the horizontal distance of these two charges from the point of pivoting it, or the point of joining the two strings together. Okay, that distance is y. So let's call this as the angle theta. Okay, so the length of both the cases are same. Okay, so this definitely will, the masses will be the charge, the balls will definitely carry some mass there. So what is the direction of weight which is acting downward, which is the direction as EMG. I'm using the same figure to make you understand it. Okay, because of that weight and the electrostatic repulsion, there will be definitely a tension on the string. Okay, now if I extend this line backward, I could find that, yes, I could find that this angle is also theta. So if I resolve this, yes, if I resolve this vector, so if I rub this and write it again, so if I extend this line a little bit more, yes, this angle is obviously, it is shown with an angle theta. So if I extend this, we could find that this is tension T. If I resolve the tension into two components, you'll find this is equal to T cos theta. You already know it. And there's another component of tension which is acting perpendicular to it, which is called T sine theta. Okay, that is T sine theta. So that is T sine theta. Now how is this going to act? There is a pitch ball here and a pitch ball here. Both are having electrostatic repulsion. Both are having positive charges. So there is an electrostatic repulsion, and the force of electrostatic repulsion is going to act in that direction, a repulsive force. So the force created by electrostatic repulsion. Since the object is in equilibrium, which is already specified, we can say that the total forces, the forces balance out. Let's write down at equilibrium. Yes, at equilibrium, we can say that the upward force, that is T cos theta, we can write it down. Similarly, what is this force? And let's write it down this first. T sine theta is equal to this electrostatic force, which is Fe. Okay, similarly the upward force T cos theta will be equal to mg. So let's divide this equation and watch out how it works out. From here you can get it as tan theta is equal to Fe divided by mg. So if I substitute the equation for electrostatic force, what will be the equation for electrostatic force? 1 by 4 pi epsilon naught Q1, Q2. Here the charges are same. So you will take it as R square, Q square divided by the distance between them. So that is what we call R square. If I substitute this, you will get it is equal to Q square divided by 4 pi epsilon naught R square multiplied by mg, which is equal to tan theta. But according to this particular figure which is shown over there, what will be tan theta is equal to? From the diagram you will be able to understand. This is the opposite side, this is the adjacent side of this right angled triangle. So how will you write it? Tan theta from that will be equal to the opposite side, which is this length. That length will be obviously r by 2, r by 2 divided by adjacent side, which is given as y. So if I equate this, you will get this is equal to r by 2y is equal to r by 2y is equal to q square divided by 4 pi epsilon naught r square times mg. So that was the equation. For y is equal to what we can write down. If I take all these terms together, you will get is equal to y is equal to, you will get it as equal to mg r cube. That means both r and r is there, r cube, it will become divided by, yes, 2 times k of q square, where I have taken k equal to 1 by 4 pi epsilon naught, that you can do it. Okay, that you will get it. So you will get y is proportional to r cube. R will be proportional to y to the power 1 over 3. So if that y becomes y by 2, then what happens to r? So let's call that r as r dash, which is directly proportional to y by 2 power 1 by 3. So what you'll get, you just have to divide those together. You will get is equal to is directly proportional. Let's put it as y to the power 1 by 3 over 2 to the power 1 by 3. So y to the power 1 by 3 obviously is r. So you can substitute that is equal to r by 2 to the power 1 over 3. So this is r dash. So obviously you got an answer for this. What is the answer? R over 2 to the power 1 over 1 by r root 3. So let's analyze this particular question. A cylinder of radius r and length L is placed in a uniform electric field in such a way that the axis of the cylinder is parallel to the electric field. So if I draw that, you will probably understand faster. So if this is your cylinder, the axis of the cylinder is this. Yeah, such a way that the axis of the cylinder is parallel to the electric field. That means this is the axis of the cylinder. At the same time, the direction of the electric field is also in the same direction. So this is the direction of electric field. What's the question is? The flux of the field through the cylindrical surfaces. What will be the flux through this particular region which is shown? Since there is no electric field in that particular direction, what you can obviously find out, the flux, since the equation for flux is equal to E dot the area of that particular sphere. Since there is no electric field through the curved part of the cylinder, so the obvious answer will be there's no flux passing through it, and the answer is 0. So let's look at this particular question. If the electric flux entering and leaving an enclosed surface, is phi1 and phi2. Obviously, from here you'll be able to identify that phi1 is entering, phi2 is leaving. The electric charge inside the sphere will be, you have to calculate what is the enclosed charge inside. Okay, you obviously know that the resultant flux will be equal to the total charge enclosed inside the Gaussian surface divided by epsilon naught. So according to our question, you have to find out what is the charge enclosed. The resultant flux is, what will be the resultant flux? The phi 2 minus phi 1 is the resultant flux. One is going in and the other is coming out. So phi 2 minus phi 1 is the resultant flux. So it's equal to Q enclosed, which I am not writing it again and again. I am writing only Q, which is actually the Q enclosed divided by epsilon naught. So the resultant answer for the charge enclosed will be equal to epsilon naught multiplied by phi 2 minus phi 1, which is a question basically from Gauss's law in electrostatics, which is also an obviously a very important question.
If you like my video, please hit that like button and share with all your friends so that someone will get a benefit out of this. So until with the next video, keep studying, keep working hard, and take care.